Hello friends, welcome to EC Academy. In this lecture, let us understand loop gain, gain stability, impedance of VCVS, which is voltage controlled voltage source. To understand voltage controlled voltage source, let us consider a non-inverting amplifier. Let us consider a non-inverting amplifier. If we say non-inverting amplifier, the input is connected to non-inverting terminal of an op-amp, and from the output the feedback is connected to inverting terminal of an op-amp. Since the input is connected to non-inverting terminal, so this type of amplifier is known as non-inverting amplifier. This op-amp has open loop gain, which can be represented as AVOL. So here AVOL is open loop gain of an op-amp, which will be having the value 1 lakh or more. So the open loop gain of an op-amp will be 1 lakh times or more. So this you need to remember always. Whenever we are taking the open loop gain of an op-amp, it will be very high. In this circuit, because of this voltage divider, some portion of output is fed back to input, and the feedback fraction that can be represented as B, and we can write B is equal to V2 divided by V out. Let us call this as equation number 1. For VCVS amplifier, the closed loop voltage gain can be given as AV is equal to AV closed loop, that will be equal to AV open loop divided by 1 plus AV open loop into B. So you need to remember this formula. The overall voltage gain, which is closed loop voltage gain, can be given as open loop voltage gain divided by 1 plus open loop voltage gain, which is multiplied with feedback fraction. Let us take this as equation number 2. So this is the formula for voltage gain. Now let us understand loop gain. Here in this formula, the second term in the denominator is known as loop gain. So we can say AVOL into B is nothing but the loop gain, because AVOL is voltage gain of forward path and B is the feedback fraction or voltage gain of feedback path. So voltage gain of forward path multiplied with voltage gain of feedback path is known as overall loop gain. It will complete entire loop. So in designing the negative feedback amplifier, the loop gain is very important. So you need to remember, to design a negative feedback amplifier, the loop gain is very much important. In practical design, this loop gain is made very large. This large loop gain will stabilize voltage gain, and it enhances gain stability, distortion, input impedance and output impedance. So you need to remember that in practical design, loop gain is made very large. So this large loop gain will stabilize voltage gain, and it will enhance gain stability, distortion, input and output impedance. Now let us understand the ideal closed loop voltage gain. So you need to always remember, for VCVS, the value of AVOL into B must be always greater than unity. The voltage controlled voltage source will work well only when the loop gain is greater than unity. If we consider equation number 2, we can write AV is equal to AVOL divided by 1 plus AVOL into B. We can approximate this equation and we can write AVOL divided by AVOL into B. So if we cancel out these two terms, we can write AV is approximately equal to 1 divided by B. We will get this condition when we have AVOL that will be very much greater than 1. Now we have ideal voltage gain and exact voltage gain. Now the exact voltage gain, the exact closed loop voltage gain is slightly less than ideal voltage gain. So we have formula for ideal closed loop voltage gain as well as exact closed loop voltage gain. If we calculate these values, the exact voltage gain will be slightly less than the ideal closed loop voltage gain. So we can calculate percentage change in ideal and exact value of loop gain by considering the formula percentage error is equal to 100% divided by 1 plus AVOL into B. If 1 plus AVOL into B is 1000, then percentage error is 0.1%. So which means the exact value is 0.1% less than the ideal value. Now let us understand the gain stability. Gain stability will depends on having low percentage error between ideal and exact values of closed loop voltage gain. So gain stability depends on having low percentage error between ideal and exact closed loop voltage gain. So smaller the percentage error, better the stability. So if we have small percentage error, we will have good stability in the amplifier. For example, if we have AVOL as 20,000 and AVOL into B as 500, percentage error will be 100% divided by 1 plus AVOL into B. So this will be equal to 100% divided by 1 plus 500. So percentage error will be equal to 0.2%. So closed loop error of any VCVS amplifier will be within 0.2% of ideal value. Now let us understand closed loop impedance. So the impedance measured from the input side is input impedance and towards output side it is output impedance. So we can find input impedance which is closed loop will be equal to 1 plus AVOL into B, which is multiplied with R input parallel with RCM. Here R in is the open loop input resistance and RCM is the common mode input resistance. So we can write closed loop input impedance as 1 plus AVOL into B, that is multiplied with R in parallel with RCM. Here R in is the open loop input resistance and RCM is the common mode input resistance. You need to remember that RCM is very large, therefore R in parallel with RCM we can approximately take it as R in. Therefore Z in closed loop will be equal to 1 plus AVOL into B multiplied with Rin. We know that 1 plus AVOL into B should be always very much greater than 1. So in this formula, if we make this term very much greater than 1, at that case we can write Z in closed loop is equal to RCM. Here we can write closed loop output impedance as R out divided by 1 plus AVOL into B. Since 1 plus AVOL into B is very much greater than 1 and R out will be around 75 ohm, therefore closed loop output impedance will be always less than 1 ohm for the practical application. This is about voltage gain, loop gain, gain stability and impedance of voltage controlled voltage source. Hope you have understood the topic. Thank you.